Okay, so let's now start the second part of this lecture. With the second part, I'm starting the discussion of chapter 5 in the companion textbook. This chapter 5 is entitled Evaluation and Validation. You see from this overall diagram that evaluation and validation are design activities that we need to perform whenever we would like to come closer to the final design. These design activities comprise the mapping of applications to the execution platforms. They also comprise the optimizations and obviously also the evaluation and the validation of certain design decisions. These activities, they have to be intertwined in one way or the other. The precise way in which we have to intertwine these different activities will depend on the particular tool flow that we are using for our design. In this course, I'm trying to present a more generic view where we are not relating to a particular tool, so therefore I'm not exactly describing how we are intertwining these different activities for a particular approach to the design problem. So at the beginning of the discussion of evaluations and validations, I'd like to try to define these terms. So therefore on this slide we have the definition of these terms. First of all, let's try to define the term validation. Validation is a process of checking whether or not a certain, possibly partial design is appropriate for its purpose, meets all constraints, and will perform as expected. So as a result, we would be obtaining a yes or no decision. As a special case, we can talk about validation that is using the techniques of mathematics. If we are having a validation with mathematical rigor, we are calling such a validation formal verification. So this is the definition, the suggested definition of the first term. For evaluation, we also find a definition on the slide. Evaluation can be defined as the process of computing quantitative information of some key characteristics of a certain, possibly partial design. So these are two different activities. They are included in the same chapter because we have overlaps between the techniques that can be used for validation and for evaluation. It does frequently happen that a technique that is good for validation can also be used for verification, and that something that is good for validation can be used for evaluation, and vice versa. So therefore, let's look at these techniques for evaluation and validation. Well, how do we evaluate different designs? Well, first of all, it's important that we remember that we have usually many different criteria, many different objectives by which we can evaluate a certain embedded or cyber-physical system. And many of the criteria are shown on this slide. We have to care about the average and worst case delay of our computations. We have to care about the power and the energy consumption. We have to care about the thermal behavior. I hope you like this graphics there. I think it's a very good indication of problems with too hot computers. We have to care about dependability, safety, security. We have to care about the cost and the size, the weight, electromagnetic compatibility, radiation hardness, environmental friendliness, etc. So we have this huge set of different objectives, and I think the fact that the set of objectives is very large can also be seen from the slide, because we have these many graphical symbols there that represent all the different objectives. Actually, there are a few objectives listed here in text form that don't even have a graphic equivalent. So this raises the question, if there are so many different objectives, how are we then actually figuring out whether one design is better than another? Obviously, it really depends on our preferences, because in certain cases one objective might be dominating, in some other cases some other objective might be dominating, but nevertheless there are obviously some cases where one design is superior than some other design. So therefore we have to figure out how we can actually compare the different designs. And that is possible with the concept of Pareto optimality. And in order to introduce Pareto optimality, I have to describe the different spaces that we're using there for comparing the different designs. More precisely, I have to define two different spaces that are important for a design problem. One is the solution space and the other is the objective space. The solution space is the space that has as dimensions the different number of options that we have there for describing our design. So for example, we can have a different number of processors, we can have different sizes for the memories, we can have different bit widths there for the buses, we can have different types of buses, etc. And all these different dimensions that we could consider here are leading to the m dimensions that we are using in the solution space. And on the slide we are calling this solution space X. On the other hand, we have the objective space. In the objective space, we are considering the average and the worst case delay. That means something that we could also call performance. We are thinking about the power and the energy consumption, the size, the weight, the reliability, etc. That means, on one hand, we have the objective space. That's a space in which we evaluate a certain design. And on the other hand, we have the solution space. That's the space where we describe a particular design with certain parameters. Now, typically, we are working in this solution space where we are taking certain decisions, but we have to figure out whether a certain decision is good or not, and therefore we need a so-called objective function which will evaluate a certain design in terms of the objectives that we are using there. And we are calling this objective function a function function f of x, which is having as dimensions the different dimensions here in our objective space. So using these definitions of these different spaces, we can introduce a notation, a notion that is telling us whether or not one design is better than some other design. In order to do this, we first of all have to assume that a certain order is available. For each objective, we must be able to compare a certain value to the other values that we have there for this objective. So, for example, if we are talking about power consumption, obviously we have to figure out that some power consumption is less than some other power consumption. But if we are talking about, let's say, colors there of our little embedded system, then of course it will be very difficult to compare, because obviously there is no such relation, let's say, between blue and red. Using this ordering, we can define what it means that one design is better than some other design. And we are phrasing this as follows. We are calling a certain vector, which in this case is a vector in the objective space, is dominating some other vector v. If this vector u is not worse with respect to any of the objectives, but better than this vector v with respect to at least one objective. So we see that for all the objectives, the corresponding components of u are less than or equal than the corresponding components of this vector v. That's the vector to which we are comparing ourselves. And there is one component for which this design is superior. In this case, we are assuming that our goal is to minimize all the objectives. So that's something that applies in the case where we talk about memory size, when we talk about energy consumption, runtime, etc. These are all cases where the overall goal is to minimize the corresponding objectives. Now, it could happen that the vector v that we're comparing ourselves to is actually a vector that is dominating this other vector u, and it could happen that neither of the two is the case. If neither of the two is the case, then we are calling this an indifferent situation because there might be one objective with respect to one design is superior, and there may be another objective with respect to which the other design is superior. If that happens, then we are calling these corresponding result vectors to be indifferent. Now, based on these definitions, we can define what it means to have a so-called optimal design point, or more precisely to have a so-called Pareto optimal design point. A solution, now defined in the design space, is called Pareto optimal with respect to the overall design space if there is no other solution in the design space such that this first design is dominated by the second. So that means a certain design point X is optimal if in the entire design space we don't find any other design that would dominate our design X. We can also define optimality in the objective space. For this, we consider a certain subset of the overall objective space. And then if we have a certain design there considered in the objective space, we are calling that design a non-dominated solution with respect to that subspace S. If that design V is not dominated by any element of S, and it's a Pareto optimal design if it's not dominated by any other solution in that solution space F. So that means the definition up here defines Pareto optimality in the design space, and down here we have the corresponding definition in the objective space. A Pareto set is a term that we are using in several contexts. A Pareto set is a set of all Pareto optimal solutions. In some contexts, we also talk about a so-called Pareto front, where a Pareto front is a boundary of the dominated subspace. So I'm going to show some examples. Over here we see one Pareto point. If we had some design in that area over here, it would be dominating the Pareto point. So then that Pareto point would no longer be actually a Pareto point. We see some other design points over here. These design points are in this area where we have worse designs, so they are obviously not optimal designs. And we have some other design points over here and down there. These are so-called indifferent design points because they are, in this case, superior with respect to one objective but inferior with respect to the other. And it's the other way around for this design point down there. It's inferior, it's superior with respect to this objective, and it's inferior with respect to that objective. Since this is so important, I would like to use another slide that again tries to highlight the concept of the Pareto set. In this case, you see all the different points here that are included in the Pareto set, and then in addition we have some other design points which are obviously not corresponding to Pareto optimal designs, so therefore they are dominated by these other designs over here, and we would not include them in the Pareto set. Repeating this again, I would like to highlight that this design point is a Pareto point if there are no other designs in that area. These are the dominated designs, and in these two areas we have the indifferent designs, and the Pareto front is actually the front that is separating the dominated points from the rest of the objective space. Okay, so in this way we know by now what we mean when we talk about Pareto optimality. So if we have to come up with a design, we should not just return one design, but we should try to analyze which designs are possible. And we can do this in the so-called design space evaluation. A design space evaluation based on Pareto points is a process of finding and returning a set of Pareto optimal designs to the user, where the user is then able to select the most appropriate design. So that means if we are using this concept of Pareto optimality, we are returning a set of design points, and then the user has to decide whether energy consumption is more important than reliability, or whether the price is more important than the physical size. These decisions cannot be automatically taken by an automatic design system. So this means by now we should know how we can compare the different designs. And now we have to start the discussion of the different criteria by which we could evaluate the partial designs. And I'd like to start with a brief discussion of evaluation of the average delay that we might find in the computation of some software. So the average delays, or average execution times, could be estimated at a very high level. That means that we could possibly try to estimate the execution time by just looking at the source code. However, this is a very imprecise method, because when we just look at the source code, we wouldn't really know how many assembly instructions we would need to implement the source code. So therefore, this technique is not very precise. If we would like to have a more precise technique, then we would need to compile the code. We would need to analyze the code in more detail. If we just constrain ourselves to working at the source code level, then the resulting values are rather imprecise. And in German, there is this standard phrase of doing some computation in terms of multiplying the number pi by sum, which is an expression that indicates that something is a very rough approximation. On the other hand, we can try to have more accurate execution times, which would then be as precise as the input data is. That means that we are actually compiling the code, we are running the code on the real platform or on some platform that has a precise timing model of the real platform. Then we would get very accurate execution times for each of the inputs, and then the only question that's remaining is which inputs are we actually using. If we have a complex system, there may be so many different inputs that it may be impossible to actually run this with all the different input values. We would get average execution times in the sense that we would get some kind of average over the different input patterns that we are using there. We can care for quite some time about the computation of average execution times. However, I would like to focus on the worst case execution times, because they are so important for real-time systems. So therefore, I'd like to start with a global view on worst case execution times. We assume that we have some program to which we apply some input data. We would also possibly start with a certain state of our computation. And then we apply a large set of input data. As a result, for each of the input data, we would be observing a certain execution time. And it may happen that some execution times are happening more frequently than others. So therefore, if we look at a kind of distribution of execution times, we would find that there are some execution times that happen very frequently, and there are some others that happen less frequently. Among all the different execution times that are feasible in practice, there is one execution time which is the largest execution time, and we call that the worst case execution time. Now, unfortunately, in general, it is not possible to compute this largest possible execution time because we will in some cases have to assume some worst case execution context, and we will in some cases have to use certain abstractions. So therefore, in general, it will not be possible to really compute the worst case execution time that can actually happen in practice. In most of the cases, we have to be happy if it's feasible to compute a so-called estimated worst-case execution time, which is a safe upper bound on the worst-case execution time. And for this estimated worst-case execution time, we have two requirements. The first requirement is that this is a safe approximation. That means the real execution time should never exceed this estimated worst-case execution time. And the second requirement is tightness. That means the difference between this execution time and the other execution time should not be too large. So this leads to the question, how can we compute these worst-case execution times? They are obviously very important for real-time systems. And there we have to accept that in the general case, we cannot compute worst-case execution times, because in the general case we would have to solve the halting problem. From the theory of computability, we know that in the general case the halting problem can not be decided. That means for a general program we cannot figure out whether or not that program terminates. And if that program does not terminate, it does of course not have any upper bound on the execution time. So therefore, in the general case, that problem is undecidable. However, fortunately, for restricted programs, we can figure out whether or not the program terminates. Also, if we have some old architectures for which a certain execution time is included in the assembly language handbook, there it's relatively easy to compute a worst-case execution time. It's more difficult for new architectures that come with caches, pipelines, interrupts, virtual memory. There it's very difficult to come up with good estimates of this worst-case execution time. If we would like to compute worst-case execution times, then we need very detailed information on both the hardware and the software. For the hardware, we require a detailed timing behavior. For the software, we require the availability of machine programs, because high-level programs don't really tell us how many cycles we need for the execution. So therefore, a detailed worst-case execution time analysis cannot be done unless we really have access to the binary machine programs. As an example, I'd like to indicate how we can perform this worst-case execution time estimation. And in order to demonstrate this computation, I'm referring to one of the leading tools in that area. That's the AIT tool that is commercially offered by a spin-off of Saarbrücken University. For this AIT tool to work, we need to start with an executable program. That means with a binary program. And from the binary program, we compute a so-called control flow graph. That means we know into which directions the control flow can diverge. Then the next step is loop transformations. If we are executing loop, then it will very frequently happen that the first iteration of the loop runs at a much slower speed than the other iterations of the loop. This is caused by the presence of caches. For the first iteration of the loop, we will in many cases fill the caches, and then for all the other iterations of the loop, we will just use what's there in the caches. So therefore, typically the execution speed of the first iteration of a loop is much less than the other executions of the same loop. So therefore, a limited so-called loop unrolling is performed, which means that we are virtually distinguishing between the first iteration of a loop and all the other iterations. This is followed by so-called static analysis, which means that we try to find out by looking at the program what would happen at runtime. And in this context, the first step there is the value analysis, which means that we try to figure out which values are we going to have in our registers, which values are we going to have in our memories at runtime. And the next step then is cache and pipeline analysis. At that time, we try to figure out what is guaranteed to be in the caches, what could possibly be in the caches, and we use that in order to figure out bounds on the execution time. I would like to briefly describe one key step that we have to use there in the cache analysis. When we talk about caches, we do in general talk about so-called set associative caches, which means that we have a memory there. This memory is being addressed by one part of the current address. This part of the current address is called the index. Using the index, we are addressing one particular row there in the cache. And then for each row, we have a number of entries that are different by values there in the so-called tag field. The tag field is describing some more significant bits there of the address. The offset field is describing a particular byte or a particular word there belonging to one of the entries that we find here in such a row. Then at runtime, we are addressing the cache, we are reading out one row, and then we are comparing in parallel among all the different so-called ways whether we have a hit there in the cache. And when we have no hit, then we have to replace one of the entries there. And one very nice technique for deciding which entry there to replace is LRU-based replacement, which means that we are removing the oldest entry there from the cache and are replacing that by the entry for which we have looked in vain. Now, in this context, it's useful to analyze what we are considering when we try to figure out what is guaranteed to be in the cache, what could possibly be in the cache, and what is definitely not in the cache. In this context, we are looking at so-called program joins. That means we have one pass there through the program that is leading to a certain so-called join, and we have another pass there in the program that is also leading to the same join. And then we are trying to look at the worst case for a set associative cache, where we assume that we have 4 different ways there. That's the case that I've also displayed up here on the slide. We have 4 different ways there in the cache. Then we assume that on one of the paths we know that the most recent entry is belonging to some variable C. The second most recent one is belonging to some variable E, and then the third most recent one is belonging to variable A, and the oldest entry is actually a copy of variable D. And then for the other program paths, we know that the most recent entry, the youngest entry, is storing this variable A. We don't really know what's in there for the second most entry, and then we know that in the worst case, these variables F and C are stored there in the cache, and in the worst case, they correspond to the third most youngest entry. And also we are pretty sure then this variable b, it's stored as the oldest entry. Then we have to figure out what is the worst case that is resulting after such a program join. And we can then see what's the worst case for variable c. Well, we know variable c is included in the cache before the join. After the join, it will still be there in the cache. But in the worst case, it could be in this entry, which is the entry number 3 if we start to count these entries on the left-hand side as entry number 1, where this entry number 1 is the youngest entry. So we know in the worst case, this variable a, or I started with variable c. This variable c is definitely stored in the cache, but it could be that this is stored in the entry number 3. With variable a, we have similar information. We know that after such a program join, it will definitely be there in the cache, but it could be that in the worst case, this is also in this entry number 3. For variable e, we are not sure whether it will be in the cache at all. So in the worst case, it will not be in the cache. Then for variable f, well, we see that in the worst case, it will not be there in the cache, but we know for sure that even after the program join, a variable d will be in this entry number 4. And how did we actually generate this current state from the states that we had before the program join? Well, if we consider the worst case, we have to assume that a variable which is missing in one of the two cases will not be there in the final state. And whenever we try to figure out in which position that variable will be, we have to assume that in the worst case it will be the oldest position. That means in order to have a correct transition from the two states that we have before the program join, we have to consider the intersection between the variables, because something that is not there before the program join will not be there in the cache after the program join. And when we consider the age, we have to consider as a worst case the maximum age. In a similar way, we can look at the best case, where when we try to figure out what's the best case, we have to look at the union of the different variables that could be there in the cache, because in the best case, C could be there and it could be there in position number 1, because the best case is the situation in which it is corresponding to the youngest entry. And for the best case in general, it's sufficient if one particular variable is present only in one of the two program paths. And the best case corresponds to the minimum of the ages. So in order to figure out what is the situation after the program join, we have to compute the union of the variables and compute the minimum of the ages. Now this is what we have to do in order to analyze the cache. Next, we have to figure out what is the resulting execution time. We are computing this resulting execution time by exploiting the knowledge that we have there for the worst case execution time for all the blocks. Using the information that's resulting here from this analysis, we know exactly what is the largest execution time for each of the blocks. And from that information, we have to try to figure out what is the largest execution time for the entire program. We do this by computing a certain objective function that reflects the overall execution time. And we do this by also modeling certain constraints that reflect dependencies between the different blocks. Before actually proceeding with a description of such a model for a particular example, I'd like to make sure that you understand the technique that we are using there for modeling the largest possible execution time. And this means that I'm now moving towards a discussion of material that is discussed in the appendix of the companion textbook. It is included there in the appendix of the companion textbook because there may be students that already know about this technique, and there might be others that don't know something about this technique, so therefore it's included there in the appendix. It's nothing that's particular for the design of embedded systems. So in this context, I'd like to introduce so-called integer linear programming models. Integer linear programming models are models in which we are using certain variables x from a certain domain of variables. And using these variables, we will have two kinds of ingredients in such an integer linear programming model. We have a cost function and we have constraints. The cost function is involving linear expressions of variables from this domain. So we see that in this case we have a linear expression in these variables. The coefficients in this case are real coefficients, whereas for the time being we assume that these variables are natural numbers. We can generalize this to integer numbers very easily, and later on we will also consider real numbers here. And then the second type of ingredient is a set of constraints, where for each constraint, that means for each j from some set, we again have a linear function, a function which is linear in terms of these variables, and this linear function then has to meet some constraint which is a constant constraint. These coefficients are again real coefficients, and the constraint, that means the other side of this inequality, is also a real number. Then the problem of minimizing this so-called cost function 1 subject to the constraints 2 is called an integer linear programming problem, or a so-called ILP problem. If all these variables are constrained to be either 0 or 1, this problem is said to be a 0-1 integer linear programming problem. As an example, I'd like to use this very simple case where we have a cost function involving 3 different variables, and we might have a single constraint. In addition, we assume that all these variables should be binary variables. They should either be 1 or 0. Then among all the possible cases, we consider only those where at least 2 of the variables have a value of 1. And for all the possible cases, we compute the cost function, and obviously this second row is the one which is leading to the minimum value of this cost function. Now, with respect to integer programming or integer linear programming, I'd like to make some remarks. I introduced integer linear programming for the case where we would like to minimize the cost function. However, if we have a technique for minimizing the cost function, then it's very easy to use that also for maximizing the cost function. All we have to do is we have to multiply the cost function by -1, and then we can easily use the same technique for maximizing the cost function. Integer linear programming is NP complete. That means the execution time will increase exponentially with the size of the problem. Nevertheless, even though the running times are depending exponentially on the problem size, it has been possible to solve problems with a good number of variables in a reasonable amount of time, depending a little bit on the number of variables and on the structure of the problem. Problems with more than 1,000 variables are solvable in a current system. As a remark, we can also replace the case of considering just integer variables there for these variables. We can replace that by real variables, and then we will be talking about linear programming. Linear programming, both theoretically and also from a practical point of view, is faster than integer linear programming. but there are certain cases where we actually require integer values. So in many cases when we would like to have, let's say, the number of processors modeled with some variables, then of course we need to constrain ourselves to integers. The case in which some of these variables are real numbers and some of the variables are integers or naturals is called mixed integer linear programming. Many years ago, these ILP models or LP problems were not considered appropriate by many colleagues because they were blaming these models to require too much computation time. However, we found out that in many cases it's very useful to initially start at least with some ILP model. If it then turns out that solvers actually take too much computation time, we can still try to introduce some heuristics. It's usually a good idea to start modeling a design problem more at a formal level and then maybe introduce heuristics a little later. There are solvers available for solving these problems. There is one public solver which is called LP-solve, and there is a somewhat more powerful commercial solver which is called Cplex, and many of the colleagues in this domain are using Cplex. So after this short introduction to integer programming or integer linear programming, like we call it, I'd like to continue this discussion of the computation of large worst-case execution times. I'd like to demonstrate using a little example how we can map the computation of worst-case execution times to such an integer linear programming problem. In this example, I'm using a little program where we are initializing two variables, and then we have a loop there, we have an if statement there, and if we would generate the corresponding control flow graph from that little program, it would look like this. We have a block of code describing the main program. That's the code that we are starting initially. And then we have a block called L1, which is the code corresponding to the first instructions that we have to execute for this for loop. Then we have a block called L3, which essentially corresponds to the tests that we have to perform here for the if statement. And then blocks L4 and blocks L5 correspond to the then and else part of the if statement. And finally, this is the code that we have to execute at the end of each loop. And L2 is the code that we have to execute before we finally quit the program. Now, using AIT, we can compute the worst case execution time for each of the blocks. And this is, for example, what AIT would compute for these different blocks for the tricore. Tricore is a processor which is used in the automotive domain. Now we can model the worst case execution time as an ILP problem. And this is what we have to do for this purpose. First of all, we are using an objective function which is reflecting the worst case execution time. So what's the worst case execution time? We know that we need 21 cycles for executing the main function, and then we are using a variable, in this case variable x2, reflecting the number of times that we are executing the main program. And then on top of that, we have the execution time for that block called L1. The number of iterations that we have, the number of executions that we have for this block are modeled by a variable called x7. And we know that for each execution we need, in the worst case, 27 cycles. And this continues on for the other blocks as well. We need 2 cycles for some block that is modeled by this variable x11, and we see over here 2 cycles. This could be either block L3 or L4, and the other contributions there are the other contributions to the overall execution time. And that means we have to try to maximize that function, and if we obtain the maximum for that function, we have computed the maximum execution time. And using constraints, we have to model the structure of this control flow graph, and these constraints are kind of Kirchhoff equations for the flow into and out of a node. I've highlighted the flow into and out of this node L1. So for example, for this node L1, we know that we are modeling by some variable x7 the number of executions of that node, and the number of executions of that node correspond to the number of times that we are branching into the node, and we are branching into the node via this edge and via that other edge. So therefore x7 minus x8 minus x6 must be equal to 0. We are executing that node exactly as many times as we are branching into the node. And also we can do the same with respect to branches out of the node. These branches are modeled by variables x9 and x10. And since we are leaving this code for block L1 exactly as many times as we are executing this block L1, x7 minus x9 minus x10 must be equal to 0. So therefore, constraints like the constraints shown in red are modeling the structure of this control flow graph, and in this way we are capturing the relations between the different variables over here, and in that way we are able to figure out what is the largest execution time. Now our solver would generate one result. The solver would generate this result. It would tell us that the worst case execution time corresponds to 6,268 cycles. And for this worst case execution time, we also have certain values there for the variables that are reflecting the number of iterations. x2 is equal to 1, well, that's the number of iterations for the main body of the program. That's something that we are starting only once. And then this x7 reflecting the number of iterations over here is 101. Well, that's obvious because for this loop we have 100 iterations and we have one final test. So the code that needs to be executed there it will be executed 101 times. So that means we also get information on the number of executions that are leading to the worst case execution time. So this concludes today's set of slides. In this second file, in the slides in the second file, I've talked about evaluation and validation. We have seen that in general we have multiple objectives. In order to compare the different designs, we need to use the concept of Pareto optimality. This leads to the concept of design space exploration based on the concept of Pareto optimality. And then we have started to consider the different objectives that we need to evaluate. I have briefly looked at the average speed, where we saw that there we can either do an evaluation at a very high level, looking possibly just at the source code, where we have a fast evaluation but a limited resolution, limited accuracy. And on the other hand, we can look at the binary code, where such an evaluation takes more time, but it would be rather precise. And then I looked at the computation of worst case execution times, where I introduced the different steps that we need to look at. I briefly talked about one idea that we are taking into account when we do the cache analysis. And also I presented the IRP model for computing the worst case execution times from the worst case execution times of each of the blocks. I think I didn't mention that this technique is called the implicit path technique, because in this technique we don't need to explicitly consider all the different execution paths. They are implicitly reflected in the IRP model. This concludes today's presentation. Thank you very much for your attention.